Welcome everyone, and thanks for inviting me and organizing this conference, this awesome conference. So, welcome to this talk. My name is Cyril Mottier, and I'm leading engineering at Hamo, a company based in Paris working on social products. Today I'm going to talk about how to make your engineering project scale. Okay? As you may know, it's a vast subject that can span various subjects like technical challenges, like people management, like organization, etc. Given the time frame that we have, I'm not going to focus on all of these topics. I'm mainly going to focus on the technical aspects of the things, and in particular on how to have fast builds, high reusability, and clear ownership. But let's start with a story, okay? A story that is actually like fairly common. It's the story of any successful business or project. It generally starts very small, like just one person working on one very tiny code base, and this is basically the smallest and the simplest organization that can exist. But then, as the project starts to succeed, a new engineer joins, okay, and then another one. And at this scale, actually, things are working very well. Like it is very easy to share knowledge and information. Like the code base is small, making changes very easy, and newcomers very up and ready very, very quickly. And the technical depth is super low. But obviously, if the project is successful, then other people start to join, and then the team grows. Because you need to hire new engineers to sustain the growth, to accelerate the pace, to fuel the growth, basically, and to build new features. And at this point, problems start to rise. Because at this scale, it's getting harder and harder to share knowledge. Like you have so many people in the team, sharing knowledge starts to be difficult. Engineers also start stepping on each other's toes, because when they modify some code, they might modify the same code that another engineer is modifying. The build starts to take a lot of time. Coding convention starts to fade away, and code duplication starts to become a thing. So in general, what happens is that you start splitting your application in multiple independent parts, okay? Where you can assign owners, to parts and sections of the application. This model, or this organization, reduces local complexity, but it actually introduces new problems, like the lack of homogeneity in the code base, a slower pace, some kind of information loss, and much more. And if your project starts to be really a success, this approach is generally scaled at a higher level, and then the problem becomes even more present and visible. And this is actually what successful applications like, let's say, Spotify, Uber, or even Snap are used to face or are still facing in mobile. And this is actually something I faced too in mobile in the past 15 years. And this is why I want to share my experience building scalable mobile projects. So the name of the conference is actually Building Scalable Mobile Projects. But if you really want to understand why I added the mobile, there are actually 3 reasons why I wanted to focus on mobile. The first one is we're at 100 makers, and it was not possible to be accepted for the call for paper without having mobile in the title, so I added mobile. The second one is obviously that most of my experience is on mobile. I've spent most of my career on mobile, and I know very much how mobile is working. But the third aspect to me is that globally mobile, or more globally rich clients, so either on the web or on the desktop, are generally much more complex to scale from an organization perspective. I'm not talking about the volume or handling the load. Obviously, the backend is probably more involved in that case, but when you really talk about a team organization point of view and a code base point of view, scaling a code base for a mobile project or a rich client project is much more difficult. And this is mostly because in the end, what we end up doing is a monolith. Like we send a single binary to the Play Store, a single binary to the App Store, and so you need to deal with that. You need to make sure that whatever you're doing is actually going to end up in a single mobile project and binary. So you could really get rid of the mobile. What I'm going to talk about is really agnostic from mobile. It's really how we can scale a project in general. Very similarly, you won't hear me or hear a lot about Kotlin or Gradle or Bazel or any kind of technology, because I think the concepts that I'm going to talk about are global, like they're not specific to any kind of technology. The idea is really to understand the overall idea of how you can scale a project. So when you start a new company, like you need to think about what you're going to optimize for, because at some point you can optimize for a bunch of things. Like you can optimize for build times, you can optimize for searchability of the code, you can optimize for performance, you can optimize for reusability, for observability, testability. Like there are a bunch of things like that you can optimize for, and like it's scary. Like it's really scary. And that's normal, like, because you're starting a new business, you need to deal with so many things, and choices made at the very beginning often remain for a very long time. They pave the way to success or failure. So you need to be really, really aware of that and focus on everything that is super vital to your business. Tackling everything is not possible, let's be honest. For many reasons. First, you can't do everything, and secondly, because some of those aspects are actually orthogonal. Like if you optimize for one, the other one is not going to be optimized for. So you need to choose, and this is where prioritization is super important. And in order to prioritize, you really need to understand the context in which you're evolving. And as an example, like I'm going to use our own example of the ammo company, which is, as I said, building social products. And this is exactly what we've done a few months ago when we started the business. We, based on our experience building apps used by millions of daily active users at Zenly when we were part of Snap, and we really focused on this to optimize the tech stack and optimize the organization to make sure that it was scalable. And when you do that, you notice that your company is actually very common in many ways and very special in many other ways. And your business, for sure, is too. So context is really the key here. So let's focus on the ammo example. What's the context of the ammo example? We're actually evolving in a super competitive consumer social ecosystem. Like we're competing against actors that are very new, very modern, like companies that are less than 10 years ago. And so we need to take that into account. The second thing is that the speed of execution in this area is super high, like really. And so your speed of execution and your ability to adapt is vital. It's really core to your survival. And finally, and this is something that was very specific to us, like where every company is going for super apps, we wanted to go for simple apps, like go back to the root of what mobile used to be. Having one app doing one thing very great, and then creating another app if you want to focus on another subject instead of putting everything in the same app. And so we want to have tons of features being reused in one app or many apps or like all of the apps that we have. And this is this context that we use to actually prioritize. And if we go back to this slide that I showed previously, it's actually a pretty exhaustive list of everything you can focus on when you start a technical project. We actually optimized for mainly 3 of them. And let's list them. And obviously, if you focus on this, you can notice that we got rid, or actually we didn't focus on most of the aspects. Like for instance, we did no focus on testability. The idea was that why bother on testability if your product is not even working? Like if you don't even have users, why do you want to test? Like it's probably too early. No cost efficiency focus. Like once again, if you have just one user, costs are going to be normally okay. If you have millions of users, then at some point you need to think about that. So we really focus on those 3 aspects. The first one being fast build times. Why? Because as I said, our ability to move fast was vital, okay? So we wanted everything to be built as quickly as possible. And our target was really sub 10 seconds for local environments. So if you press play on Android Studio or Xcode, you want to have everything on your device testable in less than 10 seconds. For an internal build, which is, because we do nightly, we want less than 100 seconds. So if you push something on the main branch, you want everything to be propagated to all of the internal testers in less than 100 seconds. And for the production, we're targeting 1,000 seconds. So in less than about 15 minutes, you want to be able to repush something completely available and ready to download to our users in less than 1,000 seconds. The second aspect, as I said, is reusability. Currently, we do advocate 2 apps, but actually, most people think that we have only 2 apps, but that's actually not true. Like, we have 2 apps that have two variants, like the instant app and the main app. They all have 2 variants. The internal build that has more features because we test them, and the production build that is the one that you can download on the Play Store, and you have the debug variant and the release variant. So if you multiply all of that, we already have 16 combination of apps, like 16 different apps. And so having this capability of reusing components between all of them very easily is super vital to us. We want to be able to enable and disable a feature just by adding or removing one line of code, or just toggling a feature toggle. And finally, ownership. Like, this is something that is going to be super important at scale, but it's also important when you're still a startup, because this is where you can assign someone that will take care of maintaining the feature, adding tests, following the crashes, fixing the crashes, making the feature evolve, etc. So it's super important, and this is something that we wanted to focus on. So those 3 aspects are the one that I'm going to focus on during this conference. What are the solutions to that? There is one solution that is obvious, that everybody knows. It's called modularization, okay? But modularization is really like a simple concept. It's a concept of separating a code base in multiple entities, each of which can be worked on independently, but that can still be combined for deployment at the end. And it's actually absolutely not new or innovative. It was introduced by an American scientist called Larry Constantine back in 1968, so it's completely not new. The thing with modularization is that just saying modularization is not going to solve your problems, because if you do it wrong, then you're introducing new problems that are even worse than the one that you used to have. So you really need to do it correctly. And the definition that Larry Constantine gave to really do modularization in a good way is to consider a structure as stable if cohesion is high and coupling is low, okay? So he introduced these 2 concepts of cohesion and coupling. Cohesion is the degree to which your internal components of a module are related, okay? So you want to make this as high as possible. And coupling is how your module depends on external modules. And you want to make that as low as possible. So you really need to maximize cohesion and minimize coupling. And when you start a project, you start modularizing a project, there are some common pitfalls. The first one being modularizing by layer versus features, or creating too fine or too coarse grained modules, or having an overly complex API surface for a module. This is generally an evidence that you've done it wrong, or depending on too many modules, or exposing overly large feature set. So these are things that you need to keep in mind. If you have that in your project, then it's probably an evidence that it's not going to scale very well. And to scale very well, as I said, you need to really focus on what you want to focus. And I said, first aspect for us was really build times. So to focus and to optimize build times, we had to understand what is actually making build times long or short. And to do that, you need to understand the tooling behind build times, and it's called the build system. And the definition of a build system is really, really simple. Generally, we consider that it's a tool to transform source code into executable programs. But if you really read this definition, like a shell script is a build system, and actually it's true, it's a build system. A make file, end file, like any kind of things that can produce, or even a compiler, is actually a build system. But if you start having a much more complex project, it's definitely not going to scale. So generally, we consider modern build system as a very different, with a very different definition. And the definition I would give to a modern build system is a tool to coordinate the execution of a reverse topological sort of a directed acyclic graph of actions. Scary, right? Let's focus on all of these aspects, and you will see that it's very, very simple. So the first notion that I introduced is the notion of directed acyclic graph. So a directed acyclic graph, or DAG, I will say DAG now, is actually a graph. So if you remember your computer science courses, it's really just a set of nodes with edges between all of those nodes. And it's directed because if you look at the edges, they are oriented, okay? So here, for instance, you have A that requires B to be executed first, and B requires C, F, and H to be executed before it can be executed itself. Okay? So the direction is super vital. And why do we say acyclic? It just means that you can't have a cycle in your graph. So let's say, for instance, that I had an edge between F and G. Sorry. Here, like, you end up with a kind of a chicken and egg problem, because if you want to build E, you need to build F, that needs to build G, that needs to build E again. So you end up like with no solution to this build system. So here, like, it's not possible. And that's why when you have a modern build system, it's always based on this notion of DAG, okay? So that was the first thing that I wanted to introduce. The second thing I talked about is this notion of topological sort. That's a scary name, but actually you will see that it's very simple. A topological sort is a linear ordering of the nodes such that every directed edge from, let's say, U to V is actually giving you an ordering where U comes before V. Okay, so in order to do that, what we do, let's say we want to build D here. So in order to build D, I said, like, you need to just follow the edges. You will need to build B and E to be able to execute, D. And to execute B and E, you will need to execute also the action C, F, and H, okay? And then you just have to go on the other direction. So now that you know that you need to build the leaves first, you will first build execute C, F, and H. Then you can remove them from the graph because they've been executed. Now that you've executed these ones, you can execute B and E. And now that you've executed these ones, you can also execute D and end up with the final artifact or the final output, or like really what you wanted from this D action. But the topological sort is just one ordering. Like, there are multiple solutions to a topological sort of a DAG, okay? So let's say, for instance, this one is actually what I would call a visual top-to-bottom ordering. Like, I just looked at C, F, H, B, and E, and D. But there are multiple solutions. So let's say, for instance, that you want to focus on F first, because F has two dependent, like there are two actions that depends on F. Maybe it's smarter to start with F first, and then C, and then H. Okay, then one solution is to, I'm going on the wrong direction. Maybe one solution is to focus on most in edges first, okay? And so one solution would be F, C, H, B, E, D. So this is this notion of topological sort. And as I said, a build system will just execute the action in this this ordering. Another thing that is super important when you build a project at scale is this notion of critical path. And in order to do that, you need to add another notion on top of the DAG, which is the notion of execution time. So let's say, for instance, it's completely random here, that for E, if you execute E, it will take 2 units of time. If you execute H, it will take 6 units of time, okay? So now that we have that, we can start executing things. And it depends really on the machine and the resources that you have. Like, let's say you have 2 workers. Like, workers can be a machine, can be a CPU, can be whatever it is, but it's an execution of something that can execute some actions. And then this is one way of ordering the tasks and ordering the action, executing the action. So I will, here, for instance, we execute C and F in parallel. Once C is done, you can build E. Once F is done, you can build H. And then because you have H, you have H yet, you can start building B. And once you have B and E, you can build D, okay? So this ordering gives you 11 units of time. If you actually start by H, because H is a huge task, you will optimize. Like, you still have the exact same dependency and ordering, but you will end up with 10 units of time, okay? And if we had a new CPU or a new machine, then we can optimize again, because we can say, hey, let's start with H on this first runner or first worker, then B and D, because this is the way to optimize. And we end up with only 9 units of time. maybe one thing would be, but let's add more runners. Like if we have 16 of them, like it would be better. But the thing is, no, it's not better, because if you look at how actions are depending on each other, you will see that H is required for B, that is required for D, and this is this notion of critical path. A critical path is really the time, the duration of the execution of the node, and you can add as many workers as you want, and you're not going to optimize. This is the minimum amount of time that is required to execute your DAG. So in this case, for instance, if you look at here, it's really D, B, and H, and there is no way to go faster than 9 units of time in this case, because it will always take at minimum this amount of time. And the final notion that is super important when you focus on a build system is this notion of caching, or more specifically compilation avoidance. Like this notion is super simple. So you need to just focus on one node, and you need to consider that every action is done or is executed in a very hermetical way, deterministic way. So you know all of the inputs and you control everything. And the input can be files, can be off variables, can be everything. The configuration of the machine, the architecture, everything can be part of the inputs. But if you really control the input, then you can try to cache the input, because if you know that the input is going to be the same, then the output is going to be the same too. So let's say like you have 3 blue circles at the input, and you output a blue square, then you can put that in a cache somewhere. Like then you have 3 yellow dots, then you have this output, you can cache it somewhere, and then you have those 3 blue dots again, and you know, because you've done it previously, that there is no need to execute A, because you know that executing A will have no side effect, and the output will be the same one as the previous execution. So you can skip completely A, not like take these 5 units of time, and just output directly what was required. And this is something that is super important, because if you look in a DAG, like a DAG is obviously in practice much bigger than that. Like it can end up, I think at AMO it's something like 100,000 nodes like that. So it's super huge. This is super vital, because let's say E is cached, is changed, the input of E are changed, then you need, and the output changes too, then you need to re-execute D and G. And if you cache, then you can say, hey, this is something that you've already seen before, the output is going to be the same for D and G, nothing to execute, because the input are still the same for D and G. So this is this notion of caching and compilation avoidance. So when you do that, once you understand that, you understand that the unwavering path that you really need to follow is first have correctly sized compilation units, because if they are too large, then there is no way to parallelize. The second thing is do everything you can to embrace compilation avoidance and caching in your project. The third thing is that if you need to have a frequency of change aware DAG. What I mean by that is if you frequently change a module, you need to make sure that it's higher in the hierarchy of the DAG. If it's at the very bottom, chances are the output will be the same, and it will invalidate all of the dependent of this module. And so you need to make sure that it's higher in the hierarchy, or at the very top of the hierarchy. And finally, you need, as I said, because of the critical path, you need to build something that is avoiding critical paths, long critical paths at all costs. And this is by creating something that is breadth-oriented, a DAG that is breadth-oriented instead of depth-oriented. And you can obviously structure the code base. In order to do that, you need to structure the code base around the code locality principle. So I will give you an example of how we've done it at AMO. So what we have is we have a monorepo. At the monorepo, at the root of the monorepo, we have like all of these directories. There is no more than this. And these directories are really split by teams, or more specifically by technology, okay, or by frameworks. So we have an Android directory for everything that is Android related. We have an iOS one for everything that is iOS related. We have RS, which is Rust, so everything that is Rust related. So in our case, it's the backend plus the backend for frontend that we have and we share between iOS and Android. We have web, obviously, for the web. So everything is sandboxed like this, so that normally, as an Android user, you will work mostly in the Android directory. As an iOS user, for our iOS developer, you will mostly focus on the iOS directory, and this is where your life will be on a daily basis. If we start opening this Android directory, you can see that there is not so many directories either. And we split that in many categories or module categories. And in our case, we split that in 4 categories. Those 4 categories are: 1, foundation. Foundation is really all of the frameworks that are extension on top of third-party libraries. Like, for instance, we have CodeNX, or we have CoilX, or we have like extension over Android or over like third-party libraries. Then we have platform. Platform is really all of the frameworks, internal frameworks that we have to build the features. Like, they're not really the features. They are not aware of the business logic or anything that we are doing specifically in the product, but they are really the building blocks from a foundation perspective or core perspective. So I can give you some example. Like we have an in-house navigation framework, an in-house deep link handling framework. We have a way to deal with crashes, to deal with bug reporting or with analytics, for instance. All of that is part of platform. It's not specific to a feature. It's something that will be reused by many features. Then you have the components module categories. Components are like another name for feature. We decided not to go for feature because when you say feature in the office, people always think about the product aspect of the feature, and we consider that components are more technical. And the good approach is that a component can be 2 features, for instance, from a product point of view, or 2 features can be done with 2 components technical side, on the technical side. And so we have 2 different names, but it's very similar. And finally, on top of that, we have apps. And apps are just aggregating components, nothing more, and injecting, and we'll see that just after, injecting what's necessary to build the app. And if you look at the components, we split that in yet other directories and other modules that are built independently. So we split settings in multiple, each component are split in multiple categories or types of modules. This is how we call it. So we have multiple types of modules. We have API, lib, and bindings. These are the 3 that are super vital. The API is just a set of interfaces and data classes, or just like strict, let's say strict, that are exposing what your component is doing and accessible from the outside. Okay, so it's supposed to be extremely lightweight and not changed a lot. Like, what you do is, most of the time, you change the implementation. And the implementation of this API is in lib. So we named it lib, but it could be imp or implementation. So this is where all of the code, the implementation of your feature lies. And this is going to change very, very often. Like, this is where engineers are spending most of their time. In order to bind all of that, we have these bindings types of module that is just a very tiny modules that we're using Dagger and Hilt, etc. But the idea is just to inject a specific or a concrete implementation of a interface or trait, and this is done in bindings. Then we have core and core bindings. I'm not going to focus specifically on it because it's super AMO specific. And then we have sample and apps. Sample is one app that can be testing or just integrating just this component so that you can start rapidly the project and test it. And apps are a very special types of modules that are only in the apps category, which is just an aggregator of components. So if we look at like the graph, so don't be afraid, like there's going to be a lot of arrows, etc. But I try to simplify as much as possible this notion. So we have foundation, as I said. These are just extensions on top of third-party libraries that we're using. Then we have platform, as I said, analytics, navigation, bug reporting, unified map, which is our wrapper around Google Map, but maybe something else in the future, but our way of having an API surface around Google Map because we're not super satisfied with it, entirely satisfied with it. And so if you look at it, inside all of these platform categories, we have different types of modules, okay? So we have always the API, so this is the API surface, and then we have a specific implementation. Like for instance, for analytics, we're using amplitude. And so we have amplitude bindings. For navigation, we're using something completely internal, so we use lib and bindings. For bug reporting, we use shake bugs. So we have a shake implementation of the API, and we have a shake binding for this one. So this is really how platform is built. On top of that, we have components, like best friend, identity, profile, settings, now playing. All of these features are completely agnostic from the app they're running in. And are also split in 3 different main types of modules: API, lib, and bindings. And finally, on top of that, we have apps. And apps are just aggregators of components and sometimes platform. So if you look at this, here we have something that is very, leveled, like many levels. And the idea is an app cannot depend on any other app. So an app is always depending on everything that is below. It's kind of a unidirectional flow. So an app can depend on components, can depend on platform, can depend on foundation, but most of the time it's only going to depend on components. Similarly, a component can depend on other components, and we will see how in the next slides, but they can always depend on what's below. So a component can depend on component or platform or foundation, same for platform. They can depend, even though we try to not do that, depend on other platform modules, but they can also depend on foundation, and foundation, they can't even rely on anything else but third-party or external libraries. So if we look at the dependency, we always have this paradigm. Like the lib obviously depend on the API for best friend, for instance, and the bindings, because it's associating the concrete implementation with the interface, it depends on both the lib that depends on the API. So we always have this pattern. Same for platform. Then I said, now playing, for instance, can depend on foundation, or a platform framework can depend on foundation. So you always have arrows going to the bottom, okay? And this is completely possible. Another way that is possible, another thing that is possible is to depend on, components can depend on platform, okay? So if they depend on platform, they do not depend on a specific implementation of a platform framework. They depend on the API of this platform framework. This is really super vital, because this is what is not going to change. And so because it's not changing, it's not going to invalidate your build time, your caching, and so it's not going to make your build times any longer. Then you can, something that will happen, like at some point, I don't know, let's say best friend depends on identity. Identity is our user management system, I would say, or user management feature. A best friend always depend on, like, let's say, what is a user ID, for instance. But this is defined as identity, and so best friend depends on identity. But once again, as you can see, it's always the implementation of a feature, of a component feature, like let's say, for instance, in this case, the best friend lib module only depend on the API module of other component. And this is really crucial, because this is how we manage to reduce the compilation time as much as possible. Because what you end up doing is to depend only on things that are not changed a lot. And finally, apps, as I said, are mostly aggregators of components. So this is what is done. So if you look at what happens if you change the implementation of best friend here, you will go through the dependent of lib. And actually, when we change lib here, only bindings is modified, and so only location is rebuilt. Like nothing else is rebuilt, everything else is just caching. Okay, so we just use the cache. If we modify an implementation of a platform framework, same. Like it just, everything that depends on this platform framework, or the bindings of it, that is going to be invalidated, and most of the time it's mostly the apps. However, if we modify an API of a component, this is going to impact more the build time. But once again, this is not a problem, because this happens maybe once every week. So if you have a longer build time once every week, and 1,000 other builds are fast, like sub 1 minute, this is completely fine. So if you modify, for instance, settings API here, everything that depends on settings API, so other components, implementation, as well as the apps, will be rebuilt. But that's okay, because it happens very rarely. Similarly, if you modify a foundation framework, because everything can depend on it, you're going to impact your build system. But once again, this is not a problem for us, because this happens very rarely. What happens is that people are working mostly in the implementation of the features, so in the lib of a component. And here, if I modify the now playing lib, obviously it will invalidate a bunch of things. The other aspect that I mentioned, because we have that now, it makes reusability super easy, okay? So the reusability is just the idea of being able to add or remove very easily like a component or a feature of an app in another app or in the same app. And so what we end up doing, like this is a bit of Gradle, but if you look at the location, so one of our app is called Bump, but internally it's called Location. If you look at the build.gradle.kts, it's just one line of code, or 2 lines. Like in the dependency block, we just have implementation, projects.components.settings.bindings, and we end up having the feature automatically added to the app. Like there is nothing else to do. Sometimes, depending on the module that you're integrating, you need to inject some stuff. Like for instance, in the case of settings, we need to add there is one footer in the settings feature that is specific to one app. This is the only thing that I need to inject at the app level. But the rest is just one line of code. And this is super flexible. Because for instance, here I have in the location build.gradle.kts, I'm integrating the avatar feature. I could also make it available here in the location instant, which is our instant app of this app. So it's actually just an aggregation of many other features. And if I want something that is only available internally, like to be able to test it without having it in production, it's just one line again. Instead of having implementation, it's called happy internal. Our internal build is called happy. So it's happy implementation, and then you have your super secret new feature that is added automatically to your app. So this makes everything very easy. And finally, ownership. Ownership is a very, very important subject. So what we have, as I said, is a monorepo, and a monorepo, like, has many advantages. I'm a huge fan of monorepos, but it's not, most of the time the tooling that we have on a daily basis are not super adapted to monorepos. And the first tooling that to me is not adapted to a monorepo is GitHub, because GitHub is, I love GitHub, but it's mostly designed for small projects that depend on each other with versioning, so it's done more in an open source model, and it's not really done for monorepos that are huge with a huge number of lines and no versioning, because actually that's the whole idea of having a monorepo. You don't have to deal with versioning because everything is in the same repo, and when you build something, you build everything, and you know that everything is aligned in terms of versioning. So why? GitHub comes with one notion called code owners. So this file is, I don't know if you're familiar with it, but it's doing the job, but it doesn't scale super well for many reasons to me. The first one that is it's using, to me, something that I call an ancient syntax that is based on .gitignore, like glob-based, and it's not super modern, like I would prefer to have regex-based or something like that. The logic is, to me, super unorthodox. Like it's not actually the first match that matches, but the last one that matches. It has a very permissive syntax. Like for instance, you can say, "Hey, I want to own all of the KT files." That means nothing. Like at a given scale, at a large scale, owning all of the Kotlin files means nothing. You can't own 1 million lines of code. That's not possible humanly. And it's not resilient at all to refactoring. Like if you move code owners won't be updated, and so your code owners is outdated, and GitHub is not telling you that it's outdated. Like it's just checking the handles or the email addresses, but it's not looking at the path, if they are valid and if they exist. And the most important problem of a code owners is that it's broken by design to me, because if everybody can modify a code owners, then nobody owns it. So the code owner is supposed to deal with ownership, but it can't even deal with ownership for its own file. And so what we've done is something that is based actually on like the shoulder of a giant. Like we did something very similar to what Chromium has, or maybe if you're familiar with Kubernetes, they have this notion of owners file. And so we created our own variant of it, because this is actually integrated in the source code. You have access to the source code of Kubernetes and Chromium, but it's not super easy to extract, so we did it on our own. It's done in Python in Chromium, and it's done in Go in Kubernetes. We did it in Kotlin. I did it in Kotlin, but it's very similar. The idea is to have a hierarchical way of defining ownership. So if you look at the owners file in the monorepo, you will see that you can add an owners file in a directory, and by putting this owners file, inside you will have the owners, you will just say all of the files in this directory are owned by this person, or those persons, if you have multiple of them. And if you look at, like, for instance, the one at the root, we are 2 people. The idea is not for us to be owners of everything, because normally in the subdirectories, you will have other owners that will be more owners than you because they're closer to the files. And if you execute the owners tool, like, there is not so many commands that you can do. You can create a new owner file, format all of owner files, or lists, or generate. Like, what we do currently is that we use those owners files to generate the code owners from GitHub, because we're not at the point where we are at the scale where we want everything to be handled on our own. So we just use these owner files because they are super resilient to code refactoring, etc. And we generate the GitHub's code owner. And what's important is obviously list. Like, you can say, hey, let's look at who's the owner of Android components clip slope, or who's the owner of iOS app clips location, or who's the owner of RS/mobile. And it will display all of the owners for this specific path. And this is something that scales super well because, once again, once you have a huge monorepo with multiple directories, you can easily assign owners to a specific directory. So in general, like, what I wanted to conclude with is that there is no solution that is perfect. Like, it's just a matter of concessions. What's important is really to adapt to your use case, okay? And really understand what you're trying to tackle and focus on what you want to tackle. Thank you very much. I said any question. I think we don't have time for questions, but I will be here for the 2 days. So if you have any question regarding my talk, feel free to say hi and come by. Thanks.